Real-time feedback into the behavior of your distributed systems and observing changes, exceptions, errors in real time allows you to not only experiment with confidence, but respond instantly to get things working again.
Hello. Today I'm going to be talking about implementing a performant URL parser from scratch. So before we start, I want to give a little bit of information about me. I'm Yagiz Nizipli. I'm a software engineer. I'm a master student at Fordham University. I'm a Node core collaborator and performance team member. I've been mainly focusing on text encoders and decoders and the performance in Node.js. I'm the creator of URL state machine and fast query string. So let's give a little bit of a background before we start into what URL parsers are and how that goes. So a little bit of a brief introduction to JavaScript runtimes. So Node.js is a runtime on top of V8 engine, the JavaScript engine behind Chromium. Just like Node.js, Dino is also using V8, and a little bit of new runtime, Bound.js is using WebKit as a runtime. So JavaScript, basically in JavaScript runtimes is that whenever you call a function, the JavaScript userland runs the C++ code using a bridge through Node.js, and the value that you retrieve from the C++ is deserialized on the JavaScript side and then presented to the user, which is the developer. So computationally, heavy functions live in C++. This means that you don't need to focus any of your code in JavaScript, but you can write it in C++ if you want to produce performant code. So let's start with URL parsers. Why URL parser matters? So this URL parsers are the most important functionality for a web server. Every single network request uses that URL parser, and it basically creates the baseline of benchmarks with any network request. So this is an example of a diagram of a request coming to a server. So it basically, on the left side, there's this person, let's say Alice or Bob. Bob submits a credential through user agent, which sends to the client. The client sends a request, submits the credentials, client ID redirect URL to authorization server, authorization returns authorization code, and then user agent redirects authorization code and client request token, and so on and so forth. So basically every arrow from left to right includes a URL, and for every left to right request, it needs to parse and understand what that URL is and what the path is. So that's where URL parsers come in. So URL parser is a very significant component, but it's too complex and leads to bugs, and that's why nobody focuses and nobody wants to focus on it. So this is one of the examples while I was working on this project, is that I thought that I found a bug, and it seems that 256.256.256 URL is invalid, and one of the libraries, WhatVGURL, recommended that actually it worked in Chrome and Safari, but not in Node.js. So this means that the initial implementation of a URL parser was somehow wrong or not up to date. So after this feedback that I got, I opened an issue, URL parsers does not validate IPv4 with more than 4 parts. This is one of the issues. URL is not compliant to specification. This is another issue created by me, and later they're all fixed. But let's talk about the goal of a URL parser. What is the goal? Basically, if you look into this diagram, you will see on the orange side is that HTTPS user pass sub example.com 8080. So basically, HTTPS is the protocol. Username password is an optional value with characters, and then host name is always there. The port If it's another special port, which is like 80 or 443, it's not required because URL parsers understand that. And then we might need some path name and search and hash. So if you look at from this diagram, you can easily say that, oh, okay, it's really easy to understand and implement URL parser, right? You just need to get, if it starts with HTTPS, if there's a user pass, what about host names, what about ports, what about path name? We want to make sure that the search is a valid one, and so on and so forth. But it's not as easy as writing a regex, and it's much more complicated. So what is the state machine behind it? There is actually a specification for writing URL parsers, and this is an example of it. This represents all of the state machines that needs to traverse in order to complete the URL parser. So if you look at it from a much more closer perspective, there is a schema start state. Scheme start state can go to no scheme state. Let's say we don't have HTTPS, or it can, if it starts with a schema state, then we need to parse that schema. What is a valid one? What are the valid ones? If it's HTTPS, then we might omit the port part because HTTPS is always 443. If it's HTTP, then it's 80. If it's SSH, so there are some special cases. And according to schema state, it can go to special authority / state, special relative authority state, or relative state. So special authority / state, which means that either I have a username password kind of combination, so I need to parse that state. If it's a special relative or authority state, it can be a file path. In Windows, it's something else, and in macOS, Unix systems, it's something else. And according to that, it can be a relative state. It can be a relative state. So it's not as easy as writing regex or understanding. So this is one of the states that are available in the URL parsing specification. So let's dive into scheme start state. So if C is a character, is an ASCII alpha, append C lowercase to buffer and set the state to schema state. So this is pretty straightforward. Otherwise, if state override is not given, set state to no scheme state and decrease pointer by 1. Otherwise, validation error, return failure. So if you look at it from this perspective, it's pretty straightforward, right? But this is one of the, I think, 20 states that are available in this specification. So let's look into a little bit more complex effort. So no scheme state. What happens if I don't have a HTTP, HTTPS, and so on and so forth? If base is null, or base has an opaque path, and C is not U, which is like hashtag, validation error, return failure. So first of all, we need to know what is an opaque path. It's all explained in the documentation. Otherwise, if base has an opaque path and C is a hashtag, set URL scheme to the base scheme, URL path to path, URL query to base, and URL fragment to the empty string. So if my path starts with a hashtag, which means that this is a fragment state, so the URL needs to go to the fragment state, and that's one of the end states. Otherwise, blah, blah. So this is what URL specification, URL parser specification is all about. But so I kind of feel like, why are we even talking about it? So the main issue that actually led me to this implementation is that there's a significant performance issue with what we URL in Node.js, and in order to update it, there was an issue opened, and I wanted to make it faster. So can it be faster? So this is one of the issues. Re-implement what we URL parser in WASM. The URL is there for you if you want to look. It was actually opened by one of the technical steering committee members, which is James Snell. He basically said that it should be possible to realize a significant performance improvement by porting the implementation to WASM. So WASM is WebAssembly. So if we implemented the URL parser through WASM, then we might get a URL parser. So this was pretty interesting to me, because right now I know what I needed to do. I need to port the implementation in a language that's performant, like C++ or Rust. And then I need to expose the API through WebAssembly so that Node.js applications can consume it. So, but before we start, let's take a step back and understand what our options are. WebAssembly is really WebAssembly our only option. The potential solutions, not for writing URL parser, but also for most of the application, is that you can either compile C++, Rust, or any other language through WebAssembly and expose the API, or you can write an API, which is Node API with C++ Rust, and you can actually run the C++ code and like expose it through the C bindings, or you can write a pure JavaScript. So we don't want to write and expose our implementation through C++ and Rust through an API, because that's the actual implementation what's happening right now. So let's start with WebAssembly then. So I chose Rust because it's proven that Rust is super performant. Actually, I wanted to learn Rust, so this is one of the emotional decisions that led to this decision-making process. But so WebAssembly and Rust is a really good duo. Thanks to Firefox, there are lots of contributions on that side. There are really great libraries, and the ecosystem is ready for mass adoption in one of the most crucial parts in Node.js. And on top of that, there was Undici. Undici is a really good example. It's backed by Node, and actually, by using WebAssembly and compiling LL-HTTP to WebAssembly, they had a 1,329% performance boost, and it was really good, and it was the basis of WebAssembly. But these are the expectations, but the reality is decoding UTF-16 to UTF-8. Okay, WebAssembly communication relies on shared memory. Okay, there's some problems with deserialization and deserialization of that data. Shared memory requires decoding and encoding. So text encoding and decoding in Node.js relies on C++, which means that we're going to use text encoder and text decoder. So why did we end up with text encoder? So a quick recap. So the goal of this presentation was that we're trying to improve the existing implementation, improving by removing the C++ bridge, but text encoding and decoding in Node.js relies on C++. So let's do a benchmark about all of those things. If we use a WebAssembly and if we use Rust and expose it through WebAssembly, this is again roughly estimations. This is not a full feature set URL parser that's written in Rust, but the Rust implementation is 24% slower for URL constructor. This is just by passing the URL and returning an object. That's it. On the other hand, on the other side, URL search param set is 86% slower, because whenever you're calling set, get, those kinds of variables, there's a C++ to JavaScript communication, which is we're using WebAssembly, but there's always a bridge between it. And for append, it's 96% slower. The main reason for URL search params is slower is that because it's actually implemented in JavaScript and Node.js, but I wanted to make sure that if it's possible to also improve the URL search params implementation too. So it means that it's 86% slower. That's a fact, not a random number. And here we are again. We're starting this presentation from scratch. Can we write a fast URL parser using JavaScript? So today I'm going to talk about the road to a fast URL parser for Node.js. My name is Yagiz Nizipli, and let's start from scratch again. So why JavaScript? So if you know, there was three main reasons that we thought, like, what are the three alternatives? We could either use C++ and Rust through WebAssembly. We could either use Node API with C++, or we could just write it in JavaScript. So existing implementation is C++. We tried WebAssembly and did some benchmarks, but it was slow. So there are no other solution that does not use the C++ bridge. So I'm kind of limited by the technology of my time as Howard Starkin. So as a result, URL state machine npm package rise. It's available through GitHub on anonric/url.js, which I will include at the end of this presentation. But it basically is a super fast spec compliant URL state machine for Node.js that's written in JavaScript, but not as fast as I would expect it to be. So this is one of the packages, the usage examples. So if you just pass the string of the URL, then it actually returns an object, which is scheme, username, password, and like you can retrieve those information. So let's do some benchmarks about the JavaScript implementation of it. There's another library called WhatWGRL, which provides the same feature set, and it's around 576% slower. URL state machines is 5-6 times faster, I guess. And the actual URL implementation provided by Node.js is that it's 85% faster than my solution. So this means that the decoding and encoding side of it, and it's slow, and JavaScript is kind of slow for these particular operations. So there are some of optimizations that I did, and I'm going to talk about those things. So using function versus class, actually up until Node 18, up until V8 9.5 or 9.7 version, if you create a class and have private variables on top of it, it was actually 55% slower. And just by converting a class to function with like function prototype kind of keywords, it makes your code 55% faster. So this is one of the first optimizations that I did. So the second thing was, if you change your conditional function to switch or if, it actually improves your code a lot. So if you have more than 10 keys in and if you're doing an if-else statement, actually converting it to switch is faster. If you have less than 10, then if is faster. So again, it depends on how your implementation is going, and you need to choose correctly and do some micro benchmarks in order to understand. But again, if V8 is if you're using a new Node version, these dynamics can change because there are micro benchmarks that are based on V8. So there's another one that's like string to number comparison. This is really important because if you want to compare, let's say, strings, how would you compare two different strings? First, you would check for if their length are equal. If their length are equal, then you would traverse every character one by one and make sure that each character is equal to each other. This means that I need to access all of these compared strings, each character one time, and then make an equal operation and then check it. So this is one of the idiomatic implementations that you need to do. So just by changing my authority, like my states from strings to numbers, which means that this is one of the changes that I did. So authority 100, scheme start 101. I had a really huge performance boost. So this is one of the changes that I did. Again, really important. One of the other things is that there is slice versus substring. Slice creates a new string, substring does not, but actually slice is faster. This is one of the examples. Instead of having substring this pointer plus 1 and this input.length, I just change it with a slice, and calculation of fragment is a lot faster. On top of that is none. So defining if it's not a number versus if it's checking for undefined is actually really costly operation. This is one of the mistakes that I did. Not a mistake, but it was mentioned directly in the URL parser specification, and I wanted to be 100% compliant to it. So in order to make it faster, right now I'm starting to diverge from the specification, and I'm trying to introduce optimizations of it. So this is what happens with all of those runtimes. If you want to make things faster, you need to find shortcuts, and those shortcuts are not always means that you are going to follow specification. And then there might be some uncode issues that might occur. And it's because you are not following the specification, it will be also super hard for you to track. So yeah, instead of saying code point and accessing to it, I just checked it for like if it's undefined. If it's not, just get the code point at character 0. And this is also a really huge boost. So instead of saying is none, then I'm just checking for if it's undefined again. So one of the, again, most important parts of optimization is memoization. If you're if you're recalculating a variable every time, if you're doing comparison many times, then if you store that variable in the memory and then access to that variable in the function callback, then again it's super fast. So this is one of the optimizations that I did. So the URL specification actually states that you need to check for if the current URL scheme is a special scheme state. So previously I was just checking if it's like if it's in an object of special schemes, then I would assume that it was a special URL. But the thing is, you just need to set these if it's a special URL or not when you are changing the URL scheme, then it's actually a lot faster. So let's do some statistics. So because of this work that I did, there's almost 2,000 lines of code was written, more than 800 benchmarks was run, and the current implementation is 99.9 perfect, spec compliant. That is 0.1%, like that one test is related to text encoders and like encoding UTF-8 and UTF-16, but it's again can be completed to 100% really easily. There were 733 successful web platform tests that was run in order to make sure that our implementation is correct. And even though I used all of I tested all of those WPT tests, it was actually 96% covered in the tests. So this means that the URL specification does not have the necessary tests to cover 100% of the code that was written, and this is I think this should be handled on the web platform tests. So performance. In terms of performance, the JavaScript-based parser was 76% faster compared to the other JavaScript implementation, but again, it was 95 and 96% slower than the native C++ implementation. So what basically is that there's a really great guy from Brooklyn that said that great power comes with great responsibility after V8 fixes this performance problem. So we're really dependent on V8 on performance, and I hope we will have some breakthroughs in the future. So a small footnote, this is a product, this whole presentation, this whole project was a product of my graduation thesis and Fordham University. And so I would like to thank William Lord from Fordham University, as well as James Snell and Mario Colina from Node.js. And thank you for that. And thank you for listening.